with me, and I just wanted to start with some pictures. Before that, is it start? I have 4 pictures to go, just like we go to the field. This is just to say what we plan, a bit of what we plan for Dragstone on the field. So this is one of the outcrops that we probably will visit first if we land in Barcelona and then drive from Barcelona to the place where we will stay. This is the Montserrat conglomerates, so the Montserrat Mountains. It's very spectacular mountain just close to Barcelona. And what is very nice about this outcrop, I mean, it's a huge outcrop, it's more than an outcrop, it's an entire cliff, is that it's as you can see, there are layers of that are resistant, separated by layers with more vegetation. And the interpretation is that this is a large alluvial fan that was fed in the left side of the picture, and that's to the southeast. And this alluvial fan was prograding towards the right into a shallow sea in the front of the Pyrenees. And this is in I think Middle Eocene, Miguel, something like that, maybe 40 Bartonian.
You mean the Montserrat?
Yes.
It goes from the latest Lutetian to Priabonian. It's
okay,
all Eocene.
All Eocene. And so you have so you see this strata here separated by layers of something finer grained. Yeah. This is conglomerate and something more fine grained. There are several cycles here. And so Miguel Garces, for instance, who is here, has dated this with his group very accurately with magnetostratigraphy. And so what we will discuss with you on this type of outcrop, that I hope to show also to Jean, is the timescale of cyclicity and the different hypotheses to say what is this kind of cyclicity associated with. Is it tectonics in the mountain on the left? Is it climate through water discharge variations, or is it sea level to the right of the picture? That's the kind of things that we can discuss. Then that's an outcrop that we've seen images from Rocio and Marine already. This is close to Arène. The Arène, there is a little valley here with the village of Arène. It's all very spectacular. This picture is probably a November or October picture a long time ago, and it's not the best day. It's a bit yeah, it's not a big sun, but what we will look at here, I mean, there are several very important things to look in this area. So you just get out of the hotel and you can look at dinosaur tracks all close to the city boundary, like fleeing from an asteroid. So that's quite impressive. And then you also have the PETM. And on this picture, I think the PETM is more or less there. It's not the best picture for the PETM. It's not the best section here for the PETM. We have the PETM here. I'll show you another picture afterwards. And here you also have an unconformity. I don't know if you see the angular unconformity between those strata being more inclined to the left than these ones. Okay. This is not a perspective effect. It's not because you're going into the valley. This is something, I have better pictures, but I just searched for that this morning, and this is the one I found the quickest. And so this is a very unconformity that you can see in the landscape, and that's these deposits, again, maybe I will call on Miguel, but I think they are, let's say, middle Eocene again, or perhaps a little earlier. That's the base of some conglomerates, whereas here we are in the very early Eocene. We are just after the PETM boundary, so there is a large unconformity, which is more due to tectonics. You know the age of those, Miguel? Is it?
No, not in detail.
It's on somewhere in the Eocene. It's not much time, but perhaps 5 or 10 million years still. And we see it in other places where actually Alex has been working a lot in the Sierra de Cis and in the Pobla de Sego areas. So we'll see that. That's a better section of the PETM. Sorry, of the PETM, of the Paleocene here, and then you have the PETM on top. So this is the Esplureda section. It's famous. You see a lot of, Rocio introduced that this morning. You see a lot of Paleosoil horizons. You see these color variations in this reddish succession. These color variations are, to my knowledge, and I'm not a specialist, interpreted as climatic variation. And this is a continental environment. So that's where we can dig and find little carbonate nodules, little nodules that you can then crush and analyze to understand carbon isotopes, oxygen isotopes, and so on. And here on top, you have a more resistant layer, which is the supposed to be, at least that's how it's been dated with isotopes as well. It's supposed to be emplaced, it's supposed to be deposited at the time or a little after the exact onset of this climatic change of the PETM. So one of the things we can discuss there is the timing of this and the modalities of how a climatic perturbation changes dramatically the depositional environment. And we also look afterwards how the recovery takes place. And this is a better sunny picture. I really want it on my in my notebook. That's a picture from the Mediano anticline. On the top of the Mediano anticline, it's a big tech structure south of Ainsa. Ainsa is a place where we will be staying here in a hotel that delivers absolutely gargantuesque aperitif in the evening. If you know the word gargantuesque, but Gargantua was a giant who actually digged the Lake of Geneva. So that's the lake. This is the view from the Mediano anticline. You see the little church here, the top of the church at least. This lake is artificial, and you see the strata dipping here, and you can feel that this is an anticline. Here is the prolongation to the north of this anticline. In the background, you have other cliff that are carbonates from the Cretaceous and the Tertiary that overthrust towards Earth. And so we have here a whole basin full of turbidite and slope deposits that was active when this anticline and the Pyrenees were forming. So we can really discuss tectonic stratigraphic interactions and facies and climate variations in this area. So this was to speak a little bit because I realize we haven't done it, but I hope we will probably convene a day or two before the trip to introduce some aspects of the local geology, because it's always difficult when you reach this place and you're in a minivan and you drive in little winding roads. It's always difficult to assimilate local names, local formation names, the ages. So we will provide an introduction to the geology, but I wanted to put a first seed of it in your minds, and nice pictures. Okay, so yesterday I stopped here at the introduction about this Okay, wait a second. I just have a call from the kindergarten. Coming back. Bonjour, j'ai vu que vous aviez essayé d'appeler. Castelltort, Sébastien. Bonjour.
Alex, you want to take over?
I'm not completely sure where Seba's just going to go with this. I might give him 2 minutes to come back.
No, it's just a joke. Just showing that researchers are also.
Okay, so I said yesterday that we have mainly these two variables for climate that are I would say primary for sedimentary rocks. I would probably think that precipitation is very, very important, because that's what delivers waters and transport sediments. But of course, temperature is a huge control on weathering. And also, I think both are linked. Obviously, they are not two independent variables. And François added also that there are other parameters that are important for climate. And I put as a reminder these remarks. François said there are paleoclimatic maps, a plethora. At the moment, there is really an explosion of flourishing of paleoclimatic maps. So a lot of people are really putting together many results from proxy analysis of past climates. And so the idea is that this really becomes a common tool for you as well, the ESRs in your research. It's always there is a resource there to tap in, is to try to look for those paleoclimatic maps. I would say take them at face value. You know, they are what they are. Be careful. They shouldn't be the Bible. It's not because you don't find something consistent with a paleoclimatic map that your observation is wrong. Maybe the map is wrong. Past maps are always interpolations. So, but still, it's really important to look at them. And you remember François actually showed some maps from, I think someone called Robertson or Aichison, I don't remember. And he said it wasn't published. So some of them are made by big syntheses in oil companies sometimes. So still also there's always a little warning when it's not published. Try to find something published, it's better. But if we already, a map is already interesting. And my second question was for today or tomorrow. Do you also have a MATLAB installed? I just have maybe if I have time, I just have a little thing to do on MATLAB, really super short. So I don't know the ESRs. You can answer me by email or by or in the conversation whether you have MATLAB installed on your computers. Okay. Here I'm going to describe this because it's just a way to speak about those climatic variations and some vocabulary. So this is actually this. I redraw this first part of the diagram, especially from Scotese, who has published this phanerozoic temperature curve in the Paleomag project. I only found it on the web in ResearchGate, and I still haven't found the publication of this. So I don't know if it's going to be published or if it's already, but it's already used in many papers. So and Scotese did a compilation of of paleo temperature. And so as you can see, so that's this curve, and I put in red what is called hot house. In black is greenhouse, and in blue we have ice house. Okay, so when temperatures drop, when global average temperature drops below 15 degrees, we can consider we are an ice house world. So this is a world, a planet Earth with ice caps. Most of the time, actually, we are in a greenhouse period. It doesn't prevent for some ice to be at the poles or glaciers to be in mountains, but this is a greenhouse, a normal greenhouse period. Is temperatures between 15 and something like 20 degrees. And when it's above 24 degrees, people call it a hot house. So that's really warm. It's 10 degrees more than today's temperature. So as you can see, it's interesting to note that every 150 million years in the Mesozoic or 200 million years, you have ice house, pronounced ice house period. In the Ordovician Silurian here, somewhere at the end of the Carboniferous, beginning of the Permian. Here, this is not an ice house. This is a little bit, this is the KT impact winter. Okay, it's not really, I think this is debated, such a spike here. This is not really clear, but apparently the world would have reached really low temperature at that time, actually the lowest. And people speak about an impact winter. I don't know if it says something to you, but for us in the 80s, we were in a Cold War when Russians and Americans were fighting each other. And the big threat at that time was not COVID or Al Qaeda. The big threat was a nuclear war. So, and people spoke about the nuclear winter. So if there was a global nuclear war, in Guerre mondiale nucléaire, then the threat was that you would have, particles, dust in the not only radioactivity, wars, guns, etc., but you would also have dust in the atmosphere and no sun reaching the Earth. So that will generate loss of vegetation, problems with agriculture, famine, etc., etc. And so in those years, there was a lot of people were working on this, and that's what people think may have happened to the dinosaurs. When the impact happened, there may have been some sort of nuclear winter, but just an impact winter, long enough to have an effect on the biota. And then there is the glaciations of the late Neogene and Quaternary, and we are actually currently probably going out of that, and we can discuss this here, or I have more presentations if you want to discuss about the current climate change. But we are somewhere here at the moment, okay, at 15 degrees between ice house and greenhouse, but probably on our way to greenhouse. We are actually in an ice house period because there is still ice caps at the poles. Here, I think I wanted to also speak about those OAEs. In the Mesozoic, you have several OAEs. This is ocean anoxic event, and then there is different OAEs with different names: OAE 1A, 1B, OAE 2, OAE 3. So François gave a definition of that, but you see they happen on this rising limb of the climate here, or rising temperature of the world towards the end of the Cretaceous. And here we'll speak about that just after, but here in the early Eocene, we also have a specific climate, very hot, not as hot as in the Triassic, but potentially very hot, and also with several hot or warm events. And since then, it's actually decreasing the temperature. The other thing I wanted to highlight on this picture is what I've put behind is several geostatic sea level curves. Okay, and I'm sorry I didn't put the legend, at least that I don't see the legend, but here you see how curves diverge, you know, back in the Paleozoic. So that's normal. It's hard to know where sea level, you know, 400 million years ago, and so there is a lot of uncertainty, I would say, not error, but uncertainty on sea level at that time. Yet, what I find interesting here is that more or less there is a pattern that seems to be the same in all three curves. So going up on the long term and then going down here somewhere towards the end of the Permian and in this area with glaciation. And they seem always, except here and actually here as well, it seems that usually when climate is cold and with ice caps, we have lower sea levels. Here for the Cenozoic, there is the Comines curve here. That's a correction. And otherwise, there is here in the background, this is Hack's curve with uncertainty on it. And you can see the sea level going up in the Cretaceous with warm climates. That's a general situation that we think is correct. Is that in the Cretaceous, sea level was going up, climate was warm, and perhaps there is a relationship with spreading centers being very active, especially in the Atlantic. Okay, do you have question on the Phanerozoic climate? This is just to give you some. You have sea level amplitudes here. It's just to give you some ideas about the Phanerozoic climate. Okay, then this is the Cenozoic. Okay, the Cenozoic is starting at the KT boundary. Actually, that I wanted to say that to some of you in their presentation. I think it's good when we speak about Bartonian times, for instance, or Maastrichtian, that we also say numerical ages. Because often some of us we work in some periods and we don't really know what corresponds, what Maastrichtian is in million years. So it's always good to give million years as well. So the Cenozoic starts here at the KT boundary, and it's made of the Paleogene and Neogene. Paleogene is Paleocene, Eocene, Oligocene, and if I'm not wrong, and Neogene is Miocene and the rest. And here we have different stages. I mean, there's a lot of events. This could take us a day to describe, but this curve here that you see in black is the curve of oxygen. It's a compilation of oxygen isotopes that have been measured in the carbonate shell, if you want, of little marine organisms in the oceans, in the deep ocean. And so we can have some sort of conversion to temperature of the ocean at depth and of the surface on the left. So temperature of the ocean is in red, and temperature of the average temperature of the Earth is here in black. And here are the isotopes. And this curve in black was first presented by James Zakos, and there's been refinement to it. But if you've read the paper by Molnar, you've seen a first version of it, and it's full of holes in 1991. Now it's complete and very high resolution, and higher resolution as we'll come to closer times, because dating is more accurate here than here, and also the records. But I think this is one of the most important curves we have, and one of the most important constraints we have in geology right now. It's it's a data that is absolutely fundamental to take into account. Below is the sea level curve of Comines and colleagues. And that's also an important one, but I would put much less confidence in the sea level curve we see below than in the climatic curve we have here. Yet the two, you can see, they follow a little bit each other. I think the curve by Comines is quite good. What I don't know about is the variations. But this climatic curve is a real huge anchor for reflection, I think, of what happened on Earth. And it's really one of the most important curves of the last 20 years. And so if we, here I've also put glaciations, that's already also in the Zakos, in one of the Zakos paper. And I've also put precipitation in continental Europe, okay? With a lot of uncertainty on precipitation, but you know, from 1,000 to 1,500 millimeter per year. As you can see in this diagram, glaciations are considered to start somewhere here in the late Eocene, and that we have full ice caps on the south pole of the Earth in the Oligocene already. Okay, then it becomes ephemeral in the late Oligocene, early middle Miocene, and become full again from here on somewhere in the late Miocene. And then we have also ice at the north pole in the Pleistocene and Quaternary. So that's when we really reach ice house. Okay, so here we are in a hot house, here we are in a greenhouse, and then finally here we are in a full ice house. Okay, this here is an important part of the curve, I find. It's rising climates, so rising temperature, rising sea level, and then declining temperature. So that's a bump or a hump, or there's anyway a rising limb and a limb going down, and the culmination here is called the early Eocene climate optimum. This culmination here is in the early Eocene, somewhere about 50 million years ago. Okay, that's when we had the highest temperature on the planet in the last times. Okay, since then temperature have just been the Earth has just been cooling since 50 million years, only cooling. There is a lot of debate as to why temperature rose in the Paleocene, Eocene. And that's a topic, I think, of major importance. There are many different hypotheses as to why this happened. One of them is North Atlantic volcanic degassing. If you sum up the size of the ridges, if you sum up their rate, you can come up with some figures that tell you that volcanic degassing is responsible for that. But there are also many other events, and yeah, there is tons of hypotheses. Honestly, it's not so easy to find out which one is the most important. But one of them is also Indo-Asia collision and degassing of CO2 by decarbonation of the whole northern Indian margin below Asia. Then there is as much debate as to cooling afterwards. Why are we cooling since then? And so one of the biggest hypotheses about this cooling is the trapping of CO2 by weathering. So when you weather continental rocks, some of the CO2 which is in the atmosphere and goes into water when it rains flows on basement rocks. And for instance, that's how you break down feldspars, plagioclase, And that's how you then create new carbonates in the ocean and trap CO2 in the form of calcite. And when you do that, if you weather carbonates, for instance, you destroy carbonate in the mountain and you reprecipitate carbonate in the ocean, that has no net effect on climate, because you use a CO2 to destroy carbonate in the mountain and you retrap this CO2 into the ocean. But if you weather new basement rocks that come to the surface, new feldspars, you bring to the surface new calcium and some magnesium, etc. And then you create new carbonates. That's an added excess trapping of CO2 that you do in the ocean, and that draw down. That's a drawdown of CO2 from the atmosphere. If you draw down CO2 from the atmosphere, you cool global climate. And so one of the big hypotheses, and this was put forward, for instance, by people like Remo and Rüdimann. We mentioned that earlier this week. Alex mentioned that this was a big thing in the 90s. This really corresponds well with the exhumation of basement rocks in the Indo-Asia collision. So the idea is that when you have a collision, first thing that come to the surface is cover rocks, and in the alpine orogeny sensulato from the Himalayas to the Alps and the Pyrenees, everywhere you had clastic, but a lot of carbonate rocks of the Mesozoic. And so you first weather those carbonates and nothing really happens. But at some point, after eroding a lot, you have basement rocks coming to the surface. And when those basement rocks come to the surface, perhaps that starts to draw down CO2 from the atmosphere, and you start cooling climate. Okay. So that's one of the hypotheses, at least. Just want now to say I'm not really able to tell you much more about the rest of the climate here as to their causes, because I haven't done the literature. But here is a big important event. That's the EOT, Eocene Oligocene transition. This is about 33 million years ago. That's when Antarctica becomes fully glaciated, fully iced, and there is a big storage of water, of ocean water in the ice cap that leads to this major sea level fall. So that's a big signal that we should find in sediments. People have looked at that a lot in the Pyrenees, for instance, because we see a big change in sedimentation in the Pyrenees, but it's not there. We see it before, and people like Miguel, for instance, have argued that it's not the sea level fall that we see here that is responsible for a lot of the continentalization that we see in the Pyrenees, but more of a local tectonic event in the west of the Pyrenees that closes the basin. And we can have we can discuss that again on the field. Then in the Oligocene, sea level is relatively low, and then in the Miocene you have, I didn't write it here, but you have a climate optimum. When we say optimum, it's a human perspective that when it's warm, it's optimal. So here is a climatic optimum. It's highest. It's higher temperature. Here is another optimum. It's relative to before and after. Okay, we don't reach much higher temperature than in the Eocene, but it's higher temperature, and it's quite warm actually. It's more than 3 or 4 degrees than today. And during the Miocene, we have this climatic optimum. It's a long optimum, but as far as I know, we don't have the hyperthermals that I'm going to speak about now. There's no such events as the PETM and others during this period. And somewhere here at 13 million years ago, it starts to cool down again with a first cooling period. And as you see, as this cooling proceeds, the amplitude of climatic variations increases dramatically. And so progressively we become in a cooler and more variable climate. Okay, so it's quite an interesting curve that during this transition here to cooler and cooler climate, we also transition to a much more changing climate at high frequency. So this must have a huge effect on landscape dynamics, landscape evolution, and sediment transport. And that's also the focus of a lot of debate. Has this cooling generated a lot of erosion, by changing climate so often from glaciers growing everywhere in mountains to then melting on very short periods? These are dramatic changes over very short periods. We are always in between two views, because here we have a view that everything is dramatic because we have a high resolution glasses. We can really see what happened. When we go in the Cretaceous, things seem to be much more boring in a way. You don't have such dramatic changes. Is it because we don't have the glasses to see that? Or is it real? We do have high resolution glasses sometimes in the Cretaceous with high resolution stratigraphy, orbital, astronomical, astrochronology, for instance, and I think we can pretend that we have a good resolution of the stratigraphic record also in those periods. And I really do think that the climate here was warmer and more boring, less changing, but I'm not sure. So this is one of the aspects I think you have to have in mind. And now I want to come back to the Eocene, early Eocene and Paleocineocene thermal maximum. In this rising limb here of climate, in this period of rising temperatures, people have detected very prominent. What people have detected first in the stratigraphic record is very prominent isotopic excursions. They have detected first when they did stable isotope analysis of those little carbonates, that there were very strong shifts, very strong perturbations of carbon and oxygen isotopes. Okay, in calcite, Ca, calcium, carbonate, and oxygen. You have calcium, carbon, and oxygen, CaCO3. So you can look at isotopes of those elements, and people have detected very strong perturbations. And what they've detected here, the first one that they've detected, is a very strong negative isotope excursion, and we don't have time to deal with that, but we can do it one day. So that's a very strong negative carbon isotope excursion, which means there is a lot of the light isotope, carbon 12, in the ocean, but also a very negative oxygen isotope. Okay, you see oxygen is negative up -1 here and +1 here. So when the curve goes up, it's a negative oxygen isotope excursion. And when oxygen becomes negative, it means that you go to warmer temperature. When oxygen becomes more positive, it means you go to a more cold temperature. This is because when you make a lot of ice, you trap a lot of the 16 isotope in the ice caps. That's the light isotope. And so your waters are heavy in 18. Okay, so you have positive delta O18, and that's cold. Negative delta O18 is warm. Okay, so the fact that we have a carbon isotope excursion and an oxygen isotope excursion means that we have a perturbation of the carbon cycle and the climate change together. And that's why the PETM, so this was found to be close to the, at this time, close to the Paleocene-Eocene boundary. And now it's actually the definition of the Paleocene-Eocene boundary, was interpreted at that time to say that we have a global warming of the ocean associated with the perturbation of the carbon cycle. Okay, so that's, maybe I'm talking a lot here, but that was a very important finding. People found that first in the ocean, and then a couple of years later. So this was found first by Kenneth Stott. Sorry, I forgot the name of the second author. Yeah, it's coming. It will come back. But in 78, and then a decade also later, Paul Koch found also the same excursion in the little teeth of rodents and mammals in Wyoming, in a continental basin, in fluvio-lacustrine sediments. And so when Koch found that in the US in continental deposits, the same excursion as in the ocean, then there was enough argument to say that actually this event was not just an oceanic event. You know, like those events are called ocean anoxic events because they've been studied mostly by paleoceanographers. But when Paul Koch found that in continental deposits, then the PETM, this event became, people understood that this is not only in the ocean, the warming, but it's also in the atmosphere. And so this was, I mean, from then on, we consider the PETM as an event when there was a release of carbon into the atmosphere in the form of, there are tons of different hypotheses, but in the form of CO2 or methane, potentially. And the release of these two components, CO2 and or methane, resulted in an isotopic excursion that is preserved both on land and in the ocean of carbon and oxygen. And it also resulted in the global warming episode. And this global warming episode took place over 10,000 years, or maybe 20,000 years, or actually maybe 5,000 years. So a very rapid event in Earth history. This trend here that we are, that is happening right now, the current global warming, is very different. It's actually much faster. In amplitude, it looks the same at the moment. So it's about the same rate of, it's about the same amount of injection of carbon that we are doing, but at a much higher rate. So there is an analogy. It's interesting to study the PETM, and it's called, I pronounced the word already, it's called an hyperthermal. So it's a very, it's going to high temperature. And we are probably now in a hyperthermal event at the moment. I mean, we are. So yeah, that's an interesting event, and then this event was brief. Sometimes you will see it is sometimes, so it was brief because then temperature came back to normal in about 100 to 200,000 years. And then this was followed by other hyperthermals that I haven't written here, but the PETM is the first hyperthermal and is the strongest. And sometimes the PETM is also called ETM1. Then just right after, there is ETM2. Then there is ETM3. And those ETMs are smaller amplitude and smaller duration. And then there's a bunch of ETMs, okay? But they all happen in the rising limb and into the early Eocene climatic optimum. Okay, so it's fascinating, I find, because we have a trend here, a tendency to warming. And this tendency is punctuated by events. Okay, but maybe it's trivial what I said, and maybe you won't be fascinated by it, but I think it's amazing that you know, there is this strong event, and then you come back to normal and you continue the tendency that you were into before. So there is a trend here which is perturbed by a very strong event, but then climate comes back to normal and you continue the trend in which you were before. So the perturbation did not change everything in terms of climate. The perturbation is just superimposed onto a climate trend that is driven by something that continues. So I think the simple study of the simple situation and concomitance of those events tells us that there is a driver here behind of this tendency, and there are other drivers of those ETMs. Maybe it's the same driver that suddenly acts in a non-linear way or in a faster way, or maybe it's a different driver that comes completely on top of it and is superimposing itself. Okay, but I personally think that's fascinating. And then it's cooling, and we have much less of those events, except of the middle Eocene climate optimum, which is another one that you should know about, somewhere at 40 million years ago. And this one is also different, and it's the last one of those hyperthermals. Okay, and it's a little different because there the warming is not brutal. It actually takes a long time to warm up, and is not so much associated with a carbon isotopic excursion, but it is associated with an oxygen isotopic excursion. Okay, also, you know, the PETM is associated with a strong biotic modification. So it had an influence on the fauna and the flora. Notably, there is the extension of several species of foraminifers in the ocean. And one of the hypotheses is that it is because of strong acidification of the ocean. So of course, if the ocean becomes more acid, that's when you put CO2 in the air. CO2 combines with water and then goes to the ocean. And these are acid ions. And that's not good. You know, you put acid to take off carbonate from your if you have acid waters in your tap waters, you need to clean sometimes with some acidity. And so the organisms who have a shell made of acid, they don't like it. So the idea is that this acidification of the ocean is due to injection of CO2 in the atmosphere at the PETM time, but also during the other ETMs, less strong. But at the PETM, it was so much that you had a strong biotic impact. And also there's the development of primates, a lot of monkeys. They developed dramatically at that time, especially in the US, on the American continent. There is tons of hypotheses how this happened, but one of the hypotheses is because, you know, even Greenland was green at this time and not icy. There was crocodiles on Greenland, and there was really a lot of vegetation. And so perhaps at that time, a lot of primates from Eurasia could actually jump from, that's an image, but they could jump from tree to tree, passing by Greenland and joining above and coming to America. Okay, so the continental configuration was such that they could go from banana to banana and join America, avoiding crocodiles on the ground. So there's a lot of I think it's fascinating also to see that those climatic events, they had an impact on the biosphere, flora, fauna, and that tells us something, that tells us a story of what the modern climate change could lead to. Of course, the world today is very different, but we can still have a story of what happened, and try to really tell this story, or try to understand this story, not to give recommendations to the society, but or to give, you know, a cautionary tale, or say, yeah, be careful, it's dangerous. We don't have to do that. We just have to tell the story and say what happened, and then the society can say, "Ooh, maybe we should be careful." Okay, so let me see the time. So this is a little bit about climate in the Cenozoic.
So,
I don't know if you have questions.
yes, for the last part of the curve where it is more variating.
Yes.
The scale of the period of those variations.
So that's the diagram below, but that's something that we've been speaking a little bit before. For instance, at 800,000 years, there is quite a change in the period of those changes. So you go from 40,000 years mostly to 100,000 years.
Okay.
So just to complete my answer, Marina, and something I forgot to say, you know, I spoke about Molnar paper, chicken and egg, which I think is a milestone in the last 40 years of geology. I think the paper by Zakos, which has another great title, it's called Trends, Rhythms, and Aberrations. Trends is, I think it says it all, you know, it says everything you have to know about climate of the Cenozoic. Trends are those tendencies, you know, to warming, cooling. Rhythms is what we are going to speak about. There's a beat of climatic cycles, regular beat. You know, it's like an orchestra. You have somebody who is doing, you know, the percussions, the drums, and you go there. You have this beat, and here is the theory. We will speak about that. You know, the orbital cycles, astronomical cycles, and here is the reality, how they combine and how this affect climate. And there are also aberrations. Aberrations, I don't know if you understand the word, but in French, aberration is also like in English. It's an anomaly. It's something that's completely out of trends and rhythms. So I don't know how you would say, Alex, a fausse note in an orchestra when you do the wrong note.
Yeah, I'm trying to think what. I mean, aberration is fine, I think.
Yeah, an aberration. So the PETM is an aberration. You know, this is completely out of what was planned. You know, if you would be a meteorologist of the at a million-year timescale, and you will be on this rising limb here, you will predict it just continues rising. But here, boom, there is a big, you know, some have called it the farting Earth. There is a huge fart of methane and CO2, a huge injection of CO2 and methane in the atmosphere that wasn't planned. Okay, and this happens here also in the Middle Eocene climatic optimum. So these are the aberrations. Now, more questions on those on this Cenozoic climate?
Yeah, I just have a quick question about the first figure. I noticed in the background there's two dotted lines around ice house, and what are those two indicating in the?
Good question. I am wondering myself now. It may be maybe a wrong copy paste of mine.
Okay, no problem.
Yeah, I think it's just I think I may have put the greenhouse ice house wrong and then tried to correct it and not finished to do it. So
Oh.
I guess this one is, oh,
It could.
sorry.
Isn't it the
No,
sea
no.
level?
Yeah, so one is sea level 0. Sorry, I just a graphic mistake. And the other one is the ice house greenhouse boundary. So I should correct this in my file. Yeah. Okay, so I've spoken about temperature mostly. You know, here I put precipitation. I want to say that we have proxies for temperature, ocean temperature. We have proxies for some sort of land temperatures, but it's hard. One big question is, how did temperature affect precipitation, and what's up with precipitation, you know, on land? And that's one of the questions of the PETM, for instance. We have this big warming, and that's already something in itself, but how did that affect temperature? And we could also ask, how did that affect almost weather? You know, as humans, in fact, we are more often concerned by weather than by climate. And so the question is, nowadays, in the current global warming, how is that going to change the weather? Is it going to be more rainy? How is it going to be more rainy on Earth? Is it going to be more rainy in Switzerland and more arid in North Africa? How are precipitation going to change? Are ski resorts going to open only in February and not anymore for Christmas? That's my concern. Are they going to close? Are they going to be closed for Easter? You know, the predictions are those ones. How is the snow line elevation going to be? All of these things are not understood. And you, as stratigraphers, you know, that's what Phil Allen was telling us often, is that much more than we think, a lot of the answers are in the stratigraphic record. But you only can find what you search, what you look for. It's rare that you find something by chance. Kenneth and Stott, that's the two authors. Kenneth and Stott, they found the PETM not because they were looking for a climate change, but they were looking for isotopes. And in the isotopes they were looking for, there was the carbon cycle and oxygen and temperature. So they were actually looking at temperature and climate. So I think we have to always have a broad, open mind to look for things and to, you know, open your eyes and look for all of these different things. Okay, perhaps since it's 10:59, perhaps we make a break of 15 minutes. I'm available for questions, but I think a break will be good, and then we can discuss about the lower diagram and the rest. I just wanted, in fact, thank you, Takis, for this question. I just wanted, in fact, to show you. Just I always like to make some a quick procrastination. What is this? In outreach, which is something you may have to do at some point in your career. So I hope we'll have opportunities to that. But let's take away. Let's take anything here. I just wanted to show you because we spoke about current climate change. So I just wanted to show you something that I've done about modern climate change. Yeah, it's in French. These are other pictures from the field. this is what I just explained before. This is the little farms in which we can see. I lost my mouse. Okay, I don't have a mouse anymore. Anyway, oh, that's annoying. Annotate. Wait a second. Okay, sorry, 1 second. Okay, we'll just go here. I'm still sharing, yeah. Yeah, that's the curve I just shown, and we've increased CO2. Just wanted to mention that. This is a model, because here vertical scale. Do you all see my my
Yes.
screen?
Yes.
Oui, pas de
Yeah.
problème.
So I don't know, probably you know this, so I just wanted to highlight for you who don't. This vertical scale here is the concentration of CO2 in the atmosphere. You see over the last 65 million years that we've been speaking about. And it's a model, because that's something hard to measure in the past. There are proxies of the partial pressure of CO2 in the atmosphere. One of them is the oxidative, acid state of the ocean. If your ocean is very acid, it means you have a certain pressure of CO2 in the atmosphere, the pressure and the concentration of CO2 in the atmosphere. But it's a model. It's actually a model by James Hansen. It's written here in very small. James Hansen. James Hansen is a climatologist, an American climatologist, really famous. There are TED Talks by James Hansen, and he's really famous because he's one of the first one who made a testimony in front of the Congress in the US about climate change. And so I think it's interesting to listen. And what's interesting is that here you have the modern concentration of CO2 in the atmosphere. Okay, we are here now, and this is where we were in the early Eocene climatic optimum, and also in the PETM. You see the concentration of CO2 in the atmosphere. So there was much more CO2 in the atmosphere in this time. So this raises the question. At the moment, we are 350, okay? And BAU is business as usual. If we continue business as usual, so if we continue like we are doing now, we are injecting a lot of CO2 in the atmosphere for many different, let's not speak about what drives that, but there are many drivers of that. And not only CO2, but also methane. And so we are going up in CO2, and we are actually very close to cross this first line, which is basically the line over which we've been in the last 35 million years. And when we cross this line, we go in this world here, the Eocene world, because this is the Eocene-Oligocene transition. So we are basically almost going back into the Eocene world. Okay, so I find it's interesting to have this as a comparison point, and to monitor. You know, this diagram is maybe actually outdated already. Maybe we're already 400 ppm. That's the 500 here, but maybe we're already 400 ppm of CO2 in the atmosphere. And it's, again, we spoke yesterday about numbers. You know, we speak about sediment fluxes in millions of cubic meter of sediment per year, etc., or water. But CO2 in the atmosphere, you know, 2000 for the early Eocene climatic optimum. We are now 400 and going up. That's one message first. The other message is about the word sensitivity. I think, you know, the sensitivity, and it's expressed here in degrees per watt per meter square. I personally don't really understand much of that, but sensitivity, qualitatively, I want to just convey a meaning here is that the Earth does not always react in the same way to change itself, and the climate does not always react in the same way to change. So when you inject CO2 in the atmosphere, let's say you inject a certain amount, a given amount, X, the reaction of the Earth might be different if you are in an ice house. So if you're in an ice house, maybe you inject X amount of CO2 in the atmosphere, it doesn't change much. But if you are already in a very warm house, maybe the reaction is different, okay? And also maybe the reaction in terms of weather, extreme climates, etc., is different. So, you know, for an analogy, for instance, I always think about that in the morning when you wake up, you may be reactive or not reactive to different triggers. You may be in a bad mood or in a good mood, you know, and if you walk barefoot in your kitchen and you walk on crumbles and you live with somebody, maybe that makes you unhappy one morning, or if your children shout, that makes you unhappy, and maybe one morning you're very cool and that doesn't make you unhappy. But we say I'm cool, it means I don't react much. Okay, and it's the same for the Earth. The Earth might be sometimes okay with perturbations, and sometimes it might be, you know, very unhappy. So we do not know two things. We do not know how is weather going to evolve in this in the modern climate change, but also in the past. How was weather evolving with increasing temperature on the trend and during the aberrations? So how does precipitation increase, etc., etc. But we also don't know how extreme was the reaction, and perhaps hyperthermal here in this state, perhaps the CO2 injection is not. Maybe there have been other CO2 injections like this one, but maybe the Earth was not so reactive. Maybe in the Miocene here there was such a CO2 injection at some point, but the Earth wasn't reactive to it. So that's what I want to convey. The how is sensitivity also evolving is a question. Okay, and is that okay for explanation? Okay, so now I just want to another. So I go to another aspect. I hope I have it here. Yes. I have just two slides here. It's a digression, but I think it's important for you. And I'm just talking about the slides I have here. These are temperatures anomalies. So here we are looking at the anomaly of temperature with respect to the mean of the period 1951-1980. So people have measured temperature on the globe from 1951 to 1980, and the average temperature on this 30 years or 29 years time scale on the globe was 14.9. Okay, and this is our zero here, and more or less what it was also here, except already in the 80s we see a little change. So more or less constant here and 14.9 degrees. And since then, we've seen temperature increasing. So for instance, 14.9 degrees is our zero. And so now, so in 2010, for instance, we have 1 degree more of global temperature. So it's already 15.9 in 2010. Okay. And what I want to highlight here is how, so there is land and sea, and both of them have different trends, but both of them increase. And what I want to highlight is the fact that, you know, it's a very trivial thing as well, but often you discuss with people and they say, oh, but this year is snowing so much in Spain, you know. Climate change, I'm not speaking about the causes of climate change. It's a warning here. But whether climate change is happening or not is not a discussion that can be based on your own observation that it's snowing today, okay? Or that it's very warm this summer, as a matter of fact. It's a discussion that can only be based on average, spatial and global averages. Because as you can see, there is a lot of variation from one year to another, okay? This winter here was much colder than this. So this year here, sorry, 2000 whatever, sorry, 1996 maybe, was much colder, almost not 1 degree, but almost 1 degree colder than this one. And this one was much warmer than this one, okay? And really, we have a kind of a goldfish memory, because we really do not have a 30 years memory of global temperature as an individual. So I really can say, for instance, for me this year, my feeling is that it's warmer, but for people in Spain, maybe this year is really a cold year, I don't know. So I just want to say that, and that's a message that when I do this outreach presentation, is that that's a message to have, is that there is the story we can tell from our own experience, but there is also the story that can be measured and looked at with long-term averages. Now, that's a long-term average over, you know, almost 100 years. And that's a little bit of a longer long-term average. So here is 1,000 years. And this is ppm of CO2 over 1,000 years here. And as you can see, it's very stable over 1,000 years. And then it rises, and the revolution starts, and then it rises even more in the recent decades. But I'm more interested in putting this into the 800,000 years time scale. Okay, that's the time scale of the Meuse river system that we look at in this ITN, for instance. So if you look at the last 800,000 years, you have ice age cycles. Okay, so this is warm and this is cold. And so we see actually the concentration of CO2, this is CO2 concentration in the atmosphere, changing with time. And temperature changes, delta O18 changes, glaciation, deglaciation. So this is glaciation, deglaciation, glaciation, deglaciation. And this happens with 100,000 years time scale, like we discussed before. Especially those cycles here are beautiful, very asymmetric. Okay, but if you look at it overall, you know, you always, here you come to 300, but you can almost make a line here. So you have this rhythm. You always have this warming and then this cooling, and this there is lines. It's all in a relatively constant range of concentration between 180 and 300, let's say. Okay, I don't know if you all agree with this, but that's the signal I see. I could say that's a bit, a regular bit that is given here by astronomical cycles. And what we see here is a measure, and it's completely out of that range. Okay, so I think it's important to have this in mind. Just for the anecdote, I was on a ski tour the other day, and I meet an old guy in the mountains, and he's waiting for his friends, and they are all 70 and 80 years old. And while we wait for the two other guys, he explains me that so we start speaking change, and so it's always difficult discussions, because he was a former entrepreneur in Switzerland, and he told me, and he said, you know, so I didn't say that I work on those topics, but he said, you know, before there was glaciers here, and the whole Earth was glaciated, and so the warming now, and this has been going up and down, and the warming now is totally normal. This is what happens to the Earth. So I think it's very delicate situations in a way, I find, because you don't want to argue. You know, it's not necessarily easy to say. I mean, we had a nice conversation before, and I didn't want to argue on top of the mountain in the sun, and there's no point. So I think so. I just said, as a geologist, we have a different story that we can see in the sediments. So it's a little bit of a way to get out of those arguments. Of course, we didn't speak about the causes, because that's another debate. What are the causes? But just about what really happens. It is not true that the Earth goes down in glaciation and deglaciation, and now we are just in a normal deglaciation. At least, perhaps I shouldn't even say it is not true. At least that's not what we observe in the data. So what we observe in the data now is that we are in a deglaciation. But the story I want to say here is that we are completely out of the trend in which we have been in the last 800,000 years. That's the simple factual story that I can tell from you know, ice cores and sediment cores and forams and global observations. You know, this is going to 400 ppm, whereas we've been always under 300 ppm in the last 800,000 years. And we can look at the record backwards. The last time we've reached those kind of things is at the Eocene Oligocene transition. But so I think it's a way to say, okay, I have another story to say. I know about another story. Okay, I don't know if you have questions on this. This was a long digression. And my computer is dying. No, now it's charging again. So let me come back to that. Oops. Okay, so I spoke about this a little bit, but now I want to speak about this last 8,000 years here, and because that's an important thing to know when you look at stratigraphic successions. And people like Luis Valero and Miguel can speak much more about this than me. But what we know, and Cécile, François also know that really well. What we know is that, and I'm sure you know about this, the configuration of the planets and satellites, the sun, the Earth, the moon, their exact geometrical arrangement has been changing, and it has been changing with some regularity. And the way these whole rotating asteroids are changing with some regularity, the way this happens influences the way the Earth is insulated over time. And because of a different exposure to our sun's radiations, then the climate evolved as well in response to these changes. And astronomers, notably Milankovic, and now one very famous, I think, Belgian astronomer, Jacques Lascar, working in France, I think, as I've been working on, is the theory and the calculations of those variations and how they can, what's their amplitude, their period, and how they can affect Earth's insulation. And so, because these are planets, and the motion of those planets and satellites is regular, people actually can do calculations back in time with some good precision, apparently. And so these are the changes, you know, they are called precession, obliquity, that's the middle line, and eccentricity, that's the upper line. And so precession, I won't go in detail, but because I don't have the diagram, just explaining is going to be hard. But precession is one way of changing the orientation of the axis of the Earth with respect to the sun. And so by changing that, you change the distribution of sun radiations between the northern and the southern hemisphere. And that is changing with a period of about 20,000 years. Obliquity is how inclined is the axis of the Earth with respect to the sun. So if it was fully vertical, let's say it like that, then you would have as much sun reaching the north and the south. If it's inclined, the north and the southern hemisphere receive different amount of sun. Sometimes the north receives more, sometimes the south receives more, and to different amounts as well. Okay, so this is changing with 40,000 years period about. These periods are changing with time as well. And then the eccentricity is more or less the distance, how the Earth, when it travels over a year around the sun, how the distance changes. So that affects, for instance, also the amplitude of summer-winter variations. Okay, I mean, all of this is super complex, but the curves here are simple, I think. And you can see they themselves have variations. So here the variations are strong, and then they're smaller here, then strong, and then smaller. Here you have a very low, and that's probably because of a combination also of those factors. Anyway, that's a regular bit, a regular astronomical bit, a cyclicity, much like the tides or winter summer, but it's a cyclicity that affects climate because it's on a long time scale. You know, winter summer is not climate, it's weather, it's yearly variation. Those things here are more than 20,000, 40,000, 100,000 years. And they also have over periodicity, you know, they can be at longer time scale, like 400,000 years, 2 million years. So this is really climate. And we can have a measurement of that here in several other proxies. For instance, sea level is changing with these climatic cycles, because these climatic cycles over the last 800,000 years did govern the building and melting of ice caps, because we are in an ice house. It also affects benthic delta 018, and it also affects what is this here? Antarctic delta temperature. The 0 is now, and it was colder 10,000 years ago, and more or less equal to now or warmer 120,000 years ago. Okay, so this is how it works now, and you can see the amplitude of sea level change that this has generated. 20 or 15,000 years ago, sea level, global sea level, was 100 meters below than today. I think Alex wants to say something about Brexit there.
Oh, I might leave Brexit for now.
So you could really cross. You could really you could do two amazing things. Is you could walk to England, or the Brits would actually have walked to France. But yeah, the climate was colder. So south of France looked very different. You know, the grotte, for instance, the Cosquer cave is a cave that was down in close to Marseille. And at that time, this cave was about 100 meters above sea level. And people were living in it, you know, away from the shore. And it's been only discovered recently because it's now below sea level. And only recently some divers who were not casually diving around, but real professional divers, they found the entry to the entrance to the cave. They dived, you know, below the rocks, and they found a fantastic place. At some point they emerged in one of the rooms. And what they found in this cave is drawings, paintings. So the paintings actually picture penguins, you know, so it was not time of pastis on a terrace in Marseille at that time. It was the time of drawing penguins and buffaloes, and you know, it was really cold in Marseille. So the climate was totally different in 10,000 years ago. So this is just for you to kind of apprehend the scale of those variations. This is very rapid. We've already been, you know, I often think about it like we had this discussion with Jean. The PTM was an extreme event, okay? But in the last 800,000 years, it's a bit like we've been through many PTMs. You know, the way I see it is that, you know, all of these rises in temperature here, they are all equivalent almost to the PTM. You know, it's a delta T of +8 degrees every time we've been rising temperature here. So there's a lot of, in a way, aberration has become the norm in the last 800,000 years. We've been cyclically through those aberrations. We've been warming climate very fast, very often, and also cooling, as a matter of fact. And like Francois was saying, we don't really know how cooling affected sediment supply. Okay, perhaps we know. I just don't have it in mind now. But it's true that in many places, I think in Greece, for instance, in the Rift of Corinth, there are good evidences of how sediment was produced and transferred and transported during those cycles. Yeah, I think okay. Again, the other message is that these astronomical cycles are not specificity of the late Cenozoic and the last 800 places where they are present in the Cretaceous. How many? There's so many of those sections with regular, very regular marl limestone alternations, very regular stratigraphic bedding. The idea is that these very regular stratigraphies are also due to these astronomical cycles, but potentially with much less impact and much less associated with much less sea level changes, because there was little or no ice. Can you just excuse me for a second? I just come back. Sorry, thank you. So that's what I wanted to say, and also I wanted to say that it's an important feature of climatic variations. It's also an important, very useful metronome, so something that can help you assess duration, at least. It's not an absolute way to date, but if you have a fixed age somewhere in your succession, and if you identify those cycles, you can then say something. If you identify, you identify 20,000 years precession cycles, for instance, in your succession, and you have one date somewhere precise, then you can assess duration by just counting the cycles. And so that's that's something that is really developing a lot. It's a long time that this exists, but it's developing a lot to try to assess duration of different things. For instance, it's used in the PETM. We can have some radiometric ages in some places. But thanks to astronomical cycles, we can also look at how long was the onset, how long was the body, how long was the recovery, and we can do that to give very precise ages, to some events. One of them is the Messinian that we've spoken about. The Messinian has amazing astronomical cycles in the Mediterranean, because the Mediterranean was at that time very sensitive to climate changes, especially because of the delivery of sediment from the Nile, making the whole Mediterranean changing between some sort of anoxic moments and more oxic moments. Miguel also has worked on this in I think southern Spain. And so this has been used a lot to assess the duration of the Messinian salinity crisis, for instance. So these are all important. And yes, if you identify, those excursions, now that they are known on this curve, if you identify such an excursion in your succession, you can actually, by analogy, you can tell the age. Okay, so it's also a relative dating method. It's not a chronometer, because it's not like dating. It's not giving you the age by a concentration, but it's giving you the age by association to the event of which we know the age. I don't know if that's clear, but if you find the PETM, you're 56 million years old, for instance. Okay, so basically we've been through some of the tectonics induced signals, but not all, because I've spoken mostly about large scale tectonics. You know, it didn't speak about earthquakes of growing faults, etc. We've been through a very long slide, more than 2 minutes for sure, on climate. And I actually hesitate to tell you see you later, because it's 12 o'clock. I think we've done a lot, and I have a completely new chapter that anyway will take more than the next half an hour. So, okay, Cécile, do you think if we make a 2 hours break instead of just 1.5? We have a long day, I think.
Exactly how you want and Jean want, of course. For
Let me
me,
check the schedule.
I don't know if one of you have a constraint, one of essay have you some constraint, but for me it's okay.
I mean, I won't drag it longer tonight because I stop half an hour now. Now I'm just thinking that we have this, okay, and then we have source to sink signal propagation.
But if you want to keep this one to Friday, maybe Jean has more time for the model also.
No, I still have a lot to say. So,
okay, sorry.
Yeah. I still have a lot to say. It's just that I think we've been talking a lot this morning, and I have the feeling not very interactive. I have the feeling we can and we closed somehow we closed the climate chapter. I think we can keep the rest for this afternoon.
Okay.
Is that okay for everyone? I'm not disappointed if you say yes, because you don't want half an hour more. I'm happy with that.